All right, welcome everyone. Let's get started. So welcome to day 3 of Calc 1. We're going to pick up right where we left off last time. So we were talking about limits, and we had just looked at an example of, our first example of an indeterminate form. And we're going to be seeing a whole bunch of this throughout the course. And particularly today, we're going to see a few more examples of this. So let's just kind of start off by remember what we did last time. So we had a function, and we were doing the limit of it. So we had the limit of, what was it? It was x minus 2 over x plus 2 divided by x minus 2. So we're doing this limit of as x approaches 2. And the function we were working with was, we had factored it a little bit, and we had gotten x minus 2 times x plus 2, all divided by x minus 2. All right, what did we do? Well, we canceled. We said, oh, there's an x minus 2 term on the top, there's an x minus 2 term on the bottom. Let's get rid of those, simplify this expression down a bit, and just look at the limit of x plus 2 as x approaches 2. And that one's not so bad. That one we just plugged in, and what did we get? We got 4. Now, why can we do that? That's the question. Why can we cancel variables like that? Normally we can't do that with a function. If we cancel a variable, we've changed the function. Well, as this little theorem says, limits are a little bit nicer. We can do that with limits. So if we have two functions, f of x and g of x, and they're the same, they're equal to each other, except at x equals a, well, the limits are unaffected. We can still do the limit of f of x as x approaches a. We can still do the limit of g of x as x approaches a, and they're actually still equal to each other. So why are these functions, let's look at this a little bit more closely. Why are these functions fundamentally different? So in this graph here, this is the graph of the function where we have the quotient. X minus 2 times x plus 2, all divided by x minus 2. And it looks like a line. Basically it is, but it has an undefined point. So it's undefined at x equals 2. On the right here in this graph, this is the graph of just the x plus 2 function, and there in this function, basically it looks the same except what's happening directly at x equals 2. So this one actually is defined at x equals 2. And that's the difference. The one function is undefined at x equals 2. The other function is defined at x equals 2. But for limits, it doesn't really matter. So if we're talking directly at x equals 2, these functions are very different. One of them's undefined, the other one isn't. If we're near x equals 2, then they are the same. And all is well. So when we're near x equals 2 in this case, we can cancel all we want, and it doesn't change the limit. So that works to our advantage. So we'll be seeing this idea. Basically, this theorem justifies why we're allowed to cancel variable terms when we're talking about limits. So we'll see that in all the examples that we're going to do is we're going to be able to cancel. Fundamentally changes the function, but it allows us to kind of simplify the limit calculation. All right, so let's try another example. We'll see that it's an indeterminate form. We'll do some arithmetic. We'll be able to cancel eventually, and then it'll be a limit that we can do. All right, so let's look at this example. The limit of 5 plus h squared minus 25 divided by h as h goes to 0. And in all these examples, there's going to be some trickery. There's going to be some algebra tricks. And this is, as we'll see, it's going to be our factor and cancel method. All right, so when we look at this thing, first thing we should try is notice that it's a rational function. Just try to plug in and see what you get. So let's do that. We're going to start by plugging in. So we'll do the limit as h goes to 0 of 5 plus h squared minus 25 over h. And as our first attempt, we're just going to say, let's plug in h equals 0. See what we get. If we get a number, good, we're done. If we get something that's undefined, then we have to do something different. So if we plug h equals 0 in, we get 5 plus 0 squared minus 25 all over 0. And it's not looking good. We see a 0 in the denominator. But let's just keep going. We get 25 minus 25 over 0. So we get 0 over 0. And that is our indeterminate form. We don't know what it does, so we have to stop. It's an indeterminate form. Might be infinity, might be minus infinity, might be undefined, might be a number. We have absolutely no idea what this limit does based on 0 over 0. So this plugging in method doesn't work. But the idea is, the goal is we want to cancel that h in the denominator. That's what's giving us the issue. So the goal is to cancel off that h term. And that's what we're going to see. We're going to multiply everything out in the numerator. We'll be able to factor out an h, and then we'll be able to cancel, which will simplify down our limit calculation. So let's try it out. Let's start again. So we're going to start with our limit here, 5 plus h squared minus 25 all over h as h goes to 0. We want to just kind of do whatever arithmetic we can do. So we see that 5 plus h squared. Let's multiply it out. And so if we do that, we get 25 plus 10h plus h squared. And then we have our minus 25 from before. And then all divided by h. And just in case you don't remember, how are we getting that 5, how are we doing the multiplication there? Well, you may have called it FOIL. So you write out the squared term as 5 plus h times 5 plus h, and then you multiply the two first terms together. That gives you 25. You multiply the middle terms together, the 5 and the h, that gives you a 5h. You multiply the outer terms together, that gives you another 5h. And then you multiply the last terms together, the two h's there, and that gives you the h squared. So just in case you don't remember how to multiply those types of things out, we have 5 plus h squared. Write it as 5 plus h times 5 plus h, and then just use FOIL from there. Once we get that, though, what we notice is that the 25 and the 25, that's just pure arithmetic. Those just add up to 0 there. 25 minus 25, they cancel out. So we can write that as the limit as h goes to 0 of 10h plus h squared all over h. And then from here, this is where we can, if we're looking at the numerator there, we can actually factor out an h. So both of those terms in the numerator have an h in it, so we can pull one of them out, So we get h times 10 plus h all over h. And now we've factored, and because of that last theorem, we can cancel off that same term that shows up in both the top and the bottom. So that's perfectly fine. Because of that last theorem, we can cancel those variables. And once we've done that, what are we left with? Well, now we're left with just this nice, simple 10 plus h as h goes to 0, which that's just a polynomial, so now we can just plug in. So we get 10 plus 0, which is equal to 10. So here we're just plugging in. So as soon as we do that canceling, the very next thing we try is just plug in and see what you get. If you get a number, good. That's it. That's the answer. And we did get a number there. We got 10. So what we're seeing in this example is we had an indeterminate limit, and the value of it ended up being 10. All right, let's try this again. So this is the factor and cancel method. Let's try another example, and it'll be with root functions. And we're going to see how to rationalize a root function like this, or an expression like this. So more algebra tricks. So we're going to see kind of the three most common little techniques here: factor and cancel, rationalizing in this one, and then one more in the next example. So we're just kind of going through all the different little techniques. All right, so we have this fresh limit to calculate. First thing we want to try is just plug in. If we get a number, then that's it. That's our answer. If we don't, well, then we have to do more. So we're going to plug in x equals 0 into our function. And we get 0 plus 25 under the square root sign minus 5, all divided by 0. Not looking good. We have that 0 in the denominator. But then we end up with 5 minus 5 over 0, which, again, it's that 0 over 0 form. It's indeterminate. We don't know what that means. So we have to stop. We can't go any further with that. So 0 over 0 is not the answer. It's undefined. It's not infinite. It's not negative infinity, because it's not a non-zero divided by 0. We have absolutely no idea what's happening here. So the technique we're going to use instead is rationalizing. So let's try it again. Plugging in didn't work. And the way we're going to rationalize is we're going to multiply by the conjugate of the numerator. And so what the conjugate is, so our numerator there is the square root of x plus 25 minus 5. So the conjugate of that is basically, it's the same. It looks the same, except we change that minus to a plus, and that's the only difference. So what we're going to do back in our, and we'll see why this works and as we go through, what we're going to do is we're going to multiply the top of our fraction here by that conjugate term. And then if we do something to the numerator, we have to do the exact same thing to the denominator. So we're going to put that square root x plus 25 plus 5 in the denominator. And really what we're multiplying here, you can think of it like a fancy 1. Some number divided by itself, if it's not 0, is just 1. All right, so let's see why this works. And we're going to multiply out the numerator to the two numerators here together. All right, so let's actually do that. Let's say we take our square root x plus 25 minus 5 term and multiply it with our square root x plus 25 plus 5 term. Again, we're going to do FOIL. So we multiply the two first terms together, and it's square root x plus 25 times square root x plus 25. So basically the square root just cancels there, and we're left with just x plus 25. Then we do the outer terms. So we have 5 times the square root. Then we do our inner terms. So we have negative 5 times the square root. And you might be able to start seeing why this is going to help us is because those two terms there are going to cancel. And then finally we have our two last terms that we multiply, the negative 5 and the positive 5. So we end up with positive 25, or negative 25 rather. So if we simplify this down, the 5 times the square root, the 5 times the square root cancels with the negative 5 times the square root. And we actually get even a little bit more. So we have a positive 25 and a negative 25. Those cancel as well. So when the dust settles, we've canceled everything we could cancel here after using FOIL and multiplying this out. We're only left with just a single x there for the numerator. So we get a lot of nice canceling when we multiply by this conjugate term. So let's fill that in. We're doing the limit as x goes to 0. We saw what happened when we multiplied the numerators together. So we just got x. And then we multiplied the denominators together. Nothing really special, so let's just leave that as x times the square root term plus 5. And what we're seeing now is we get some more canceling. So we get out our red pen, and we can cancel the x. We can cancel the x in the denominator. And what do we have? Doing the limit as x goes to 0. We're left with just 1 in the numerator, and then square root x plus 25 plus 5 in the denominator. And as soon as we do that canceling, step, the next thing we should do after we've rewritten the simplified expression is to just plug in again. So when we plug in, we're plugging in 0 for x. We get 1 over 0 plus 25 plus 5, all in the denominator, which ends up simplifying to just 1 over 10. So again, as soon as we do that canceling, we cancel the variable terms in the top and the bottom. The very next thing we try is just plugging in again, and hopefully it works. And it does here. We don't get another indeterminate form. All right, so this is just another example of one of our kind of standard algebra techniques called rationalizing the expression. Let's try another one now where we'll look at a common denominator. And the common denominator will kind of, again, simplify the expression, allow us to cancel, and then we'll be able to kind of finish off the limit by actually just plugging in. Okay. Yeah, this one. Yeah, this one looks good. So we're going to compute this limit. It's the limit of 1 over x minus 1 over 2 all over x minus 2 as x approaches 2. And where we're going to use this common denominator is we're going to use it up here. We have two fractions that we're trying to add or subtract. And the way to deal with that is to just try and get them into one single fraction. So instead of 1 over x minus 1 over 2, we're going to try to get that into one fraction. But let's just kind of start with our usual, can we plug in x equals 2 here? Try it out, see what happens. If we get a number, then good, we're done. If we don't get a number, if we get 0 over 0, then, doesn't work. But let's try x equals 2. What happens when we plug it in? We get 1/2 minus 1/2 over 2 minus 2, 0 over 0, no good. So indeterminate again doesn't work. So we're going to try this other technique. All right, so let's rewrite our limit here. Limit of 1 over x minus 1/2 all over x minus 2 as x approaches 2. And let's get a common denominator for those two little fractions up top. So we're going to rewrite this as the limit as x approaches 2. And our common denominator is just going to be 2x. So it'll be 2 over 2x minus x over 2x. So the quickest way to get a common denominator is just to multiply the two of them together. So in this case, it's just 2x. Once we do that, we can combine them into one single fraction up there. So that's what common denominators allow us to do. So we get 2 minus x in the numerator all over 2x. That's just up top. And then we get all over, and I like to make a big fraction sign just to kind of keep everything, orderly there. And then I put the x minus 2 in the denominator. That was originally there. Now, what we're seeing is kind of this stacked fraction that can get a little confusing. We're dividing something and then we're dividing that, so it gets a little bit confusing. So it might help to kind of rewrite this as two separate fractions, just to make it look a little bit easier to work with. So we'll take the top fraction, the 2 minus x over 2x, and then instead of dividing that by x minus 2, we're just going to multiply by the reciprocal of x minus 2. So we'll multiply by 1 over x minus 2. And that just makes it a little bit easier for us to kind of work with things. It's not absolutely necessary, but it, visually it looks a little nicer to me. All right, so now we want to cancel. The goal is we want to cancel off the term that's giving us 0 in the denominator. And what we can do is we're seeing some similar terms here. We're seeing this 2 minus x, and we're seeing an x minus 2. So those are almost there. We can almost cancel those off, but not quite. So to finish it off so that they're exactly the same, they're slightly different here, we're going to just reverse the order of the subtraction. And the way we can do that is just by multiplying by a -1. So if we multiply that denominator term by -1, what do we get? The first fraction stays the same. Whoops, we're not going to do anything to that. So it's 2 minus x here. So we'll multiply by the -1s in that second fraction. So we'll get a -1 up top. And then when we distribute that -1 into the x minus 2, it just reverses the order. So it'll be 2 minus x. And when we have that reversed, now those two terms match up nice and perfectly there. Both of them are 2 minus x's. So we get out our red pen and we can cancel those off. They're gone. So it's always good to cancel. when we can. And what we're left with the limit as x goes to 2 of -1 over 2x. And then as soon as we do our canceling, very next thing to do, we try plugging in. So as soon as we cancel that term in the denominator that was giving us a 0, very next thing we do is plug in. If we get a number, great, we're done. So we get -1 over 2 times 2, which is -1 over 4. And so the limit here, we plugged in, we get a number, and that's our answer. So -1 over 4 is, it's not undefined, it's a perfectly good number. So that's it. So again, we've started with what we saw was an indeterminate form, 0 over 0. We did some algebra there, and it ended up being able to cancel the term in the denominator that was giving us 0, and then continuing on, we were able to see that the limit was just a number. So in this case, -1 over 4. So this is just one of our other techniques. If you see a lot of little fractions in your limit, maybe try combining them by getting a common denominator. That might help. So we just sort of have this grab bag of little techniques that we can use here and there to help us do these limits. All right, let's look at one more. And this is where we have a piecewise function. So we're going to see how to handle a piecewise function. All right, so we're going to do the limit of this function f of x as x goes to 20. And we see that there's really two pieces of our function. There's the 100 plus 12x piece, and that is defined for x greater than 0 but less than or equal to 20. And then we have the square root 180 minus 4x, and that's defined for x greater than 20. And we want to do the limit as x approaches 20. So let's just kind of first consider our number line, our x-axis. And we're interested in what's happening around x equals 20. So there's a left side and a right side. And on the left side there, that's where x is less than 20. And on the right side, that's where x is greater than 20. So we could think of the x values, again, those are the inputs of our function. And let's see what the output of our function is for each of those different pieces. So when x is less than 20, if we go up to our definition of our function, we're looking for where x is less than 20, and we see it right there. So our output for the left side is given by 100 plus 12x. Now at x equals 20, the behavior of our function is changing. And so if we look on the right side, this is where x is greater than 20. And we see that right here in our definition of our function when x is greater than 20. And when that's the case, the output of our function is 180 minus 4x, all under a square root sign. So we see that the function, why we call it a piecewise function, is it's defined differently for different inputs, different pieces of the number line. All right, so let's calculate the limit of this function as x goes to 20. And for piecewise functions, the way we do that is by breaking it down into the left-hand limit and the right-hand limit. So let's start with the left-hand limit, 20 minus. And so this is our left-hand limit, and this happens when x is less than 20. So we're getting closer to 20, but with numbers that are slightly smaller. So when x is less than 20, the piece of our function that we use is the 100 plus 12x. So, and that's what we saw right here. When x is less than 20, we use that 100 plus 12x. Now that's just a polynomial, so the way we do the limit is by just plugging in. So we get 100 plus 12 times 20. Just a nice simple function that we can plug into. And what do we get? We get 340. So 100 plus 240, 340. All right, so that's the left-hand limit. Now let's try the right-hand limit. So this is how we do limits of piecewise functions. We have to break them up into the left-hand and the right-hand sides and consider each separately. So we're going to do the right-hand limit of f of x as x approaches 20 from the right. Now for a right function from the right side, that's where x is just slightly bigger. It's close to 20, but just we've added a little bit more onto it. So x is greater than 20 over there. And so we have to use the piece of our function that's given for when x is greater than 20, and that's our square root. So we're doing the limit as x approaches 20 from the right, and now on the right side, our function is that square root. So 180 minus 4x. That's a square root function. So we know from our limit laws that we can bring the limit underneath the square root sign. And then from there, the 180 minus 4x, that's just another polynomial. So now we can plug in. So when we plug in, we get the square root of 180 minus 4 times 20, which is equal to the square root of 180 minus 80, which ends up being square root 100, or 10. And so if we compare the left-hand and the right-hand limits here, the left-hand limit was 340, the right-hand limit was 10. Those are very different numbers. So we can say then that since the left-hand limit does not equal the right-hand limit, the overall limit of our function as x approaches 20 does not exist. And we usually abbreviate that DNE, does not exist. So in order for a limit to exist, the left-hand and the right-hand limits have to be the same. Okay, so really that wraps it up for just our investigation of limit laws and using those to calculate limits. In the next section, we're going to be looking at learning outcome L4, and this has to do with the idea of continuity. So we're going to first see what that definition is, and then we'll determine and explain why a function is continuous or not, and then use that idea of continuity to help us calculate limits. And it's really going to simplify down our limit calculations for a lot of cases. All right, so let's first look at the definition. So we kind of have two definitions here. We have our limit definition and then our intuitive definition. So first, let's read through the limit definition. It says a function f of x is continuous at x equals a, provided the limit of f of x as x approaches a is equal to f of a. So what this definition does is it extends the idea that we saw with polynomials and rational functions from earlier, in that we're just able to plug in. And so really what this definition is saying is that the limit is really telling us about the behavior of our function f near x equals a. When we plug in, that's telling us the behavior of our function directly at x equals a. And for a function to be continuous, those two behaviors have to be exactly the same. They have to be equal to each other. So the limit of f of x, that describes what's happening when we're near x equals a. And then when we plug in, that's telling us what's happening directly at x equals a. And for a continuous function, they're the same. So the intuitive definition is kind of relates to the graph. So if we were to draw the graph of a continuous function, we would see that it does not have any breaks or gaps, or jumps or holes in it. So a continuous function, basically you can draw it without taking your pen off the page. So if we were to draw the graph of a function, if we could just do it in one nice, smooth, one continuous motion without ever taking our pen off the page, then it's continuous. So let's just kind of look at the little graph above. That's a continuous function. And so let's just trace over it. And what we see is that we can trace over it without ever having to take our pen off the page. There's no jumps, there's no holes in it. That's a continuous function. So to check for continuity, we really use the limit definition, and there's really three things we need to check. So if we wanted to check whether a function was continuous at x equals a, there's really three things. We need to check that our function is defined. We need to calculate our limit, make sure that exists. And then finally, those two values have to be exactly the same. So they need to be the same. So there's going to be kind of three things when we have a function that we check. We first make sure it's defined, then we do the limit, make sure that exists, and then we just compare those two results and make sure that they're equal to each other. But before we get to that, let's just see why this idea of continuity is very nice and what it does for us. So that's what we're going to see in this example. This example shows us why we're going to be interested in determining the x values where a function f is continuous. All right, so let's look at this. We're going to compute the limit of natural log of x squared plus 4 divided by 5 square root x minus 2, and we're doing the limit as x approaches 1. And we're told that the function is continuous at x equals 1. So let's just write out what that means. So what is the limit definition of continuity at x equals 1? Well, it means the limit of our function f of x as x approaches 1, the way we calculate that limit, we can just plug in. So we plug x equals 1 directly into our function. And that's what continuity means. So that's what we're going to do here. We're told that this function is continuous at x equals 1. We're told that here. Normally that's something we have to check, but here we're given that. And so to calculate this limit, all we do is we plug in. So we get natural log 1 squared plus 4 all over 1 squared plus 4 all over 5 times square root 1 minus 2, all inside the natural log function there. And if we simplify that down, we get natural log 5 over 3, and that's it. That's our limit. So if we know our function's continuous, then we can just plug in and be done with the limit. So that's why we're interested in finding those x values where a function is continuous, because we can just plug in then. So it's not always going to be the case. So we're going to see functions that are not continuous. So you can't just plug in. But if we know a function is continuous, then we're good. We can just plug in. All right. So let's just see some examples, though, of what can go wrong with continuity. So in these two graphs, well, I kind of spoiled it, so spoilers. We're going to determine whether these functions are continuous at x equals 2 or not. And we're going to use the limit definition in our discussion. So a few things we want to check. Let's start with the one on the left first. We're going to see if our function's defined there. So g of 2, we want to plug x equals 2 into this function. And when we do that, we see the filled in dot at 0.23. So the value of our function at x equals 2 is actually 3. So our function is defined, so that's good. Then we want to consider the limit of our function as x approaches 2. Now in this case, as we approach from the left and from the right, we're approaching this other point, which is 2, 1. And so the limit of that function, or the limit of this function, g of x as x approaches 2, is the y value of that point. So it's equal to 1. And if we compare the results here, if this function was continuous, these had better be equal to each other, but they're not. They're not equal. So what we're seeing here is this function, we call it discontinuous at x equals 2. It's not continuous there. And you can kind of see that if you imagine kind of tracing over the graph. We start on the left and we get to that open circle. We have to take our pen off the page. We don't want to fill that in. Then we have to put it down up here. Then we have to take our pen off the page again. And then we put it back, and then we continue on. So as you're kind of tracing over that curve, you have to literally take your pen off the page, pick it up, and then draw the dot, then pick that up, put it back down, and keep going. And so we're seeing that this function is discontinuous at x equals 2. All right, in the next graph there, very similar, but in this one, you know, the limit of our function in this case is still equal to 1. but now there's no filled in circle, so our function is actually undefined at x equals 2. So that automatically means our function is discontinuous. It's not continuous there. And again, if you imagine just kind of tracing over that graph, you have to take your pen off the page to sort of just jump over that little hole there and keep going. So it's discontinuous at x equals 2. Now, we sometimes classify the types of discontinuities. So in both of these cases, we call these a removable discontinuity. And that's because we could just redefine our function, basically just plug in the hole, and all would be well. So if we just redefined our function and say in this one, just kind of said, okay, at x equals 2, let's define it to be that. We could define our function so that it is continuous. So in these cases where it's just a little hole in our graph, we call that a removable discontinuity. All right. Now there's more dramatic cases, as we're going to see. So let's look at the one on the left there. And here we see a break in the graph. So this one's more dramatic. So let's first start by just seeing if our function's defined. So when we plug 2 into our function, we look for the filled in dot, and that y-coordinate is 2. So g of 2 is equal to 2. So that's good. Our function is defined. That's always good. Then we go and do our limit. So we want to do the limit of g of x as x approaches 2. And this is where we need to do the left and the right-hand limits. But what we're seeing is that on the left, it's doing one thing. On the right, it's doing something completely different, and they don't match up. So in this, the limit does not exist. And that's because the left-hand limit does not equal the right-hand limit. So in this graph, again, it's discontinuous at x equals 2. Because our limit's undefined, so the limit does not equal the actual value of our function. And in this case, we classify this, we call it a jump discontinuity. And that's because the graph, imagine tracing over it, it jumps up. So we start, and then we have to take our pen off the page, put it back down, and we keep going, and we've actually jumped vertically there. So we call it a jump discontinuity. One more example just to see, functions that are not continuous, that are discontinuous. And this is sort of the most dramatic case here. We want to see if our function's defined. It's not. There's no filled in dot there at x equals 2, so it's undefined. We want to try to calculate the limit as x approaches 2, and we saw this last time. This is an infinite limit, so we say the limit is equal to infinity. The graph on both sides is going up and up and up, so it just keeps getting taller and taller, so the limit is infinite, which technically means does not exist. So our function is not defined, the limit does not exist, this thing does not stand a chance for being continuous. So it's discontinuous at x equals 2. And we sometimes call this one an infinite discontinuity. again, if you imagine just kind of tracing over the graph with your pen, we start on the left, we keep going, and then eventually I'm going to just keep drawing and drawing and drawing, and eventually at some point I'm going to have to take my pen off the page and then put it onto the other side and then bring it back down and keep going. So eventually I do have to take my pen off the page in order to draw that graph. So we call that first one a jump discontinuity. The other one's sort of like an infinite jump. So we call it an infinite discontinuity. All right, so just a few examples there for what can go wrong when we're talking about continuous functions. Now let's look at it a little bit more algebraically. We're going to determine if this function is continuous at x equals 20. And if we look at the graph, we kind of have a suspicion that it is. So imagine tracing over this graph. We start on the left, and yeah, there's a bend to it, but we never have to take our pen off the page in order to draw the graph there. So we have some suspicion that it is continuous, but let's check this out algebraically using limits. So first thing we want to do, plug in, make sure our function is defined. So we want to plug in 20 into this function. And so to do that, we look for where it's a piecewise function. So we're looking for the piece that tells us what happens when x is equal to 20. And we see that right here. That's telling us what happens when x is equal to 20. We plug in to that corresponding piece of our function, which is the 100 plus 12x. So we'll plug 20 in for x. And when we do that, we get 100 plus 240, which is 340. All right, so our function is defined. So that's good. Next, we need to worry about the limit. And so this is sort of similar to that example we had just looked at for doing limits of piecewise functions. And so what we want to check is the limit of our function c of x as x approaches 20. And in order to do this, we have to consider both the left and the right-hand limits. So let's do our left-hand limit first. We're going to do the limit of c of x as x approaches 20 from the left. When we approach from the left, that means x is less than 20. And so when we're deciding which piece of our function to use, we look for the x less than 20 piece, and there it is, x less than 20. So we're going to use the 100 plus 12x as the piece of our function. Now it's just a polynomial, so we can just plug in. So we get 100 plus 12 times 20. And so we get 340 if we do the arithmetic. So polynomials we can just plug into. So that's one side of our limit. Now we need to check the right side. So we're going to use x greater than 20. And so for x greater than 20, we go to our piecewise function and we look for the x greater than 20 piece. And that says we're going to use 180 plus 8x. So the limit of this function c of x as x approaches 20 from the right, we're going to use that 180 plus 8x. Now that's also a polynomial, so we can just plug in. So that's also a nice polynomial. So when we evaluate that, it just comes down to just plugging in. So we know polynomials are okay to do that. So we get 180 plus 8 times 20. And if we do the arithmetic, we also end up with 340. So those two values are the same. So if the left hand and the right hand limit are the same, then the overall limit is equal to that common value. So the left hand limit and the right hand limit are the same here. So we had to do each of those separately, but since they gave us the same value, it allows us to say that the overall limit then is that value, 340. And then finally, we just compare. And what we see is that the value of our function, 340, is equal to the limit of our function, 340. And so because those are the same, our function is continuous. So the limit of Cx as x approaches 20 is equal to C20. Those two values are the same. The function is continuous. Directly at x equals 20. And we kind of had an idea that that was going to be the case by looking at the graph. The graph, there was no jumps or breaks or holes in it. So we had a suspicion that it was going to be continuous. And here we've actually confirmed that with limits and algebraically. All right. So let's try a few more examples of those where we're just given the formula for a function and we just want to check if it's continuous or not. So we saw one just there with a piecewise function. Here we have a rational function, and we want to determine whether this function is continuous at x equals 3. So our function here is x squared minus 5x plus 6 over x minus 3. First thing we need to do, just try plugging in. So we're going to try, we're interested about continuity at x equals 3. So just try plugging 3 into the function. Make sure it's defined there. So when we do that, we get 9 minus 15 plus 6 over 3 minus 3. Simplifying, we get 0 over 0. That's undefined. So f of 3 is undefined. And we can stop. That automatically means it's discontinuous. So this function is discontinuous at x equals 3. We don't even have to do the limit. So the limit here is not necessary for us to check because our function is undefined. If we wanted the practice, we could do it. But as soon as we see that our function is undefined, we're done. We already know that it's not continuous. So that's why I generally recommend you try plugging into the function first, just to see if you get something that makes sense out. If you get division by 0, if you get 0 over 0, it's undefined and the function is automatically discontinuous then. So that's it. Discontinuous at x equals 3. We've solved that one. Let's try another one. So here another piecewise function. We're given the function 1 over x minus 3 if x does not equal 3. And then we're defining it to be 0 when x is equal to 3. And we want to see if this piecewise function is continuous or not at x equals 3. So we start off the same way. First thing we do, just make sure the function is actually defined. So we plug in. So we want to do f of 3. Now, this is saying, when we read this, this is saying x is equal to 3. So we find the piece of our function that is telling us what happens when x is equal to 3. And we're saying that that is equal to 0. So this actually is defined. So that's good. That sort of passes the first test. The function is actually defined at x equals 3. So then we want to go on and do the limit of our function as x approaches 3. And if we start it off, let's say let's start with our left-hand limit. X approaches 3 from the left. If we just plug in so for our left-hand limit, we're saying x is slightly smaller than 3. So x is less than 3. So for our left-hand limit, x is less than 3. That's really up here in this first piece of our function. So there is when x does not equal 3. So really there's kind of like two inequalities there. X less than 3 or x greater than 3. So if x is less than 3, the way our function is defined is the limit, well, we're doing the limit. It's defined as 1 over x minus 3. So on the left side of our function is 1 over x minus 3. So now we just do this limit like we've been doing in all the previous sections so far. First thing we try is just to plug in. So if we plug in x equals 3, what do we get? We get 1 over 3 minus 3, which is 1 over 0. And so division by 0 is no good, but at least it's not 0 over 0. So this is one of our c over 0 forms, which actually does tell us something. Tells us it's an infinite limit. And so the limit is either going to be plus infinity or minus infinity, and we have to decide which one. Is it positive or negative? So 0 over 0, that one's no good, indeterminate. But 1 over 0, that actually does tell us some information about what the function is doing. It's an infinite limit. So what do we do next for infinite limits? Well, we pick a little test number, plug it in, and see if we get a positive or a negative result. So for our test number, x is less than 3, so I might use something just a little bit smaller than 3, so maybe something like 2.9. We plug that into our function, and we get 1 over 2.9 minus 3, which is 0 or 1 over 1 over negative 0.1. So we don't really care about the numbers, we just care about the sign. So it's negative, 1 divided by a negative, so the result is negative there. And so the left-hand limit is minus infinity. And that's enough to show that the overall limit technically does not exist. We don't have to go any further. We don't have to do the right-hand limit. So as soon as we get an infinite limit, we've basically determined what happens with our function, or with what happens with continuity. So technically the overall limit does not exist. And so this is discontinuous. at x equals 3. Yeah, the function's defined, but on the left side, we have an infinite limit. Now, on the right side, we didn't do that, but it turns out we also have an infinite limit over there. But it's enough to just show that we have an infinite limit on one side for us to conclude that this is discontinuous at x equals 3. Okay. So it turns out that most of the functions we are going to look at in this course are continuous. And so we're going to be lucky most of the time. So we have this list here. All of these elementary functions on this list are continuous on their domains. So polynomials, they're always continuous. Every single x value, it's continuous at. And the way we denote continuous everywhere is with interval notation, and in particularly the interval from minus infinity to infinity. This is all real numbers. So polynomials, they're always continuous, so we can always evaluate their limit by just plugging in. Same thing with rational functions. Rational functions are, for the most part, polynomial divided by a polynomial, they're for the most part continuous with a little exception. And we just need to be careful where the denominator is equal to 0. So rational functions, and those are the ones we've seen a lot of examples of, most of the time they work out, but we just have to be careful where the denominator is equal to 0. Root functions, so if we have an even root, then it's continuous on its domain from 0 to infinity. So again, with even root functions, we cannot have negatives under the square root sign or even root sign. Usual example is square root. So we can't do negative square roots. If we have an odd root function, well then that's perfectly fine, and the domain of that odd root function is all real numbers. So it's continuous over all real numbers. Same thing for our most common trig functions, sine and cosine. They're continuous everywhere as well. So there's no breaks or jumps or holes in the graphs of sine and cosine. And we know tangent is related to sine and cosine, sine over cosine. So it's continuous everywhere as well, except we've introduced division, and so tangent is continuous everywhere except where, again, the denominator is equal to 0. And in our case here, that's cosine x. And cosine x is equal to 0 for plus or minus pi over 2, plus or minus 3 pi over 2, and so on. So there's a whole bunch of individual isolated spots where tangent is undefined and so discontinuous, but for the most part the graph is continuous everywhere except those places. Then there's also secant and cosecant and cotangent, so you might want to consider those as well. And those are all defined in terms of sine and cosine. Inverse trig functions, the domain of inverse sine and inverse cosine is -1 to 1. And then the domain of inverse tangent is all real numbers, and so inverse tangent is continuous over all real numbers. Same thing with our exponential functions, so like e to the x, that's continuous over all real numbers. There's no jumps or breaks or holes. And then for natural log, that's another one where we have to be a little bit careful. we can't plug 0 in, and we can't plug negative numbers into the natural log function. So we can't plug negatives or 0 inside the natural log function. So it only works if we're plugging in a positive number. And so that's its domain, 0 to infinity. But the function is continuous then on that domain. So all of the most usual functions we're going to be looking at are continuous on their domains. And so it's nice. It's going to simplify. If we can come up with some reason why a function's continuous, then that's going to really simplify down our limit calculations. So let's try an example. We're going to do the limit of h squared plus 2h plus 3 over 4h plus 5 as h goes to 0. And if we look at this function, this is a rational function. It's a polynomial divided by a polynomial. So this is a rational function. Let's figure out what its domain is. So the domain of this rational function is all real numbers except, and we have to throw out the numbers where our denominator is equal to 0. And in this case, the denominator is equal to 0 at h equals negative 5.4, or 5 over 4 rather. So the domain of this function is all real numbers except where the denominator is equal to 0. All right, so we've identified that this is a rational function. We've identified its domain. It's all real numbers except that one particular one. And then the number that we're approaching, h is approaching 0. Well, h equals 0 is in the domain. So the way we can calculate this limit then is, because of all of that, we know it's a rational function. We know its domain is everything except negative 5 over 4. And we know the number h is approaching here is in the domain. That all of that tells us that our function is continuous. At h equals 0. We know rational functions are continuous on their domain. We've identified the domain, and we've shown that the number h is approaching for our particular limit here is in that domain. So to calculate our limit then, we can just plug in. So by our continuity at h equals 0, plugging in just gives us 0 squared plus 2 times 0 plus 3 all over 4 times 0 plus 5, which simplifies to just 3 over 5. So if we know our function's continuous, then we might have to do a little bit of an argument there about why it's continuous, but then that really makes calculating the limit then that much easier. And just real quick, when we talk about the domain here like this, another way to describe the domain is using interval notation. So I could write this as the interval from negative infinity to minus 5 over 4, union with the interval from negative infinity, or negative 5 over 4 to positive infinity. So it's basically all real numbers, except I've removed that negative 5 over 4 from the middle of the interval there. So I use that little u as a union symbol, and I'm kind of gluing together those two intervals. All right, so that's a good place to stop. And we'll kind of pick it up next time for we kind of have all these little functions, all these little pieces of functions that we can work with. And we'll see that continuity also works very nicely with algebra. So we can add, subtract, multiply, divide continuous functions and still get a result that's continuous. So we'll look at that more next time. All right, so everyone have a good rest of your day, and we'll see you all on Thursday. And for Thursday, like I said, we'll finish this lecture, and then we'll continue on with the next topic, which is limits at infinity. So we'll see